make this 100%. Very easily. How? If it was my consulting firm, I could get this, I could be 100% accurate for this piece. How?
Being more certain.
What's that?
Being more certain.
No.
Data. Reporting less fields as gushers.
Reporting less fields as gushers? No.
Well, if you report only the fields you're completely certain about as a gusher, then, you know, if you change your measurement.
Nope. You've got it backwards, actually. What I'm saying is I can drive this number up to 100%. What I'm saying is anytime I'm at a gusher, I will report it as a gusher. But there's only one way to guarantee that.
Don't report until after.
Exactly. And actually, basically not reporting the dry fields is the same thing as saying every single field I'm going to report on, I'm going to report as a gusher, right? So that would dry. In that case, every single gusher would be identified as a gusher, and you get 100%. But what would that do to accuracy here?
No.
It would go to 0. Yes. So there's a trade-off here, and you do have to balance these two. Okay. So yeah, I know.
It's too late for that.
True. So this is the actual formula. I put this in because I find this much more clear.
Evan, break.
Yeah, I know. So let me draw it for you. That usually helps a little bit. Okay. So what we're trying to do here is say we have this structure. We have an event B, and then we split that up into events, or we split up the sample space like this. Okay? Now, we're interested in the probability of, say, A1 happening, given that we know B is happening. So that means we know we're in this area here, yes? Everybody agrees with that? We know we've landed here. What is the probability we also get A1? Well, it's this area divided by all of B. Yeah? Everybody remember that? Alright. So all this is really just a manipulation of that. Because we then take that overlap, this piece, and we divide by this piece. That's all we've done there. Then we apply the multiplicative rule. You remember that the probability of A and B is the probability of A given B times the probability of B. Or vice versa. I mean, it doesn't matter which way you're going. So, probability of B given A1 times the probability of A1. So this is then the probability of being here, given that this has happened, times the probability that A1 has happened. Now, we just split apart this area. Instead of saying, okay, this is just the probability of B, we're saying we're going to add together that piece, plus this piece, plus this piece, plus this piece. That's what we're doing there. And then finally, we're doing the exact same thing as up here, and just substituting in the multiplicative law. So I know this looks daunting, and that's why I just put it up there so you've at least seen it once. But now we're going to use an example, and then hopefully it'll be slightly more clear. Are there any questions before we do that? No? All right. At this point, my sense is that it's more of a, well, let's hope we get it at the end of the example rather than, oh no, this is completely clear. Yeah.
Can you leave the formula up there for a bit?
Yeah.
Thank you.
notes are right?
What's that?
These notes are all right.
And my solution to the example will be up shortly as well. So you don't have to take, extensive notes, just enough so that you understand. Is that all right, or are we still working?
Just a second. We're good.
All right. So that covers the concepts of today. We're going to illustrate trees shortly and do more tables. We've used Venn diagrams. Laws of probabilities. Sum of the probabilities of all known overlapping events must be 1. Every probability must be non-negative. Few terms we have to use: events, experiments, point sample space. Any questions on those? All right. I know this causes questions, but so this is what we use in order to count both poker and the number of ways we can put together boards, the number of ways we can put together people to see doctors. Conditional probability and independence, key. If you're going to remember one thing from today, actually, independence is probably the single most important thing. And then let's do an example for Bayes' theorem. But before we do that, just take 3 minutes at the very least to reoxygenate.